Okay, so welcome to this video, which is concerned with the consistency proof of extremum estimators, which we in this context adapt to or have a special look on GMM. Now, this is what we depicted in the lecture, this plot. You should have it in your notes. And this chart actually depicts graphically the idea behind the consistency proof for this type of estimator. And note a couple of things which are necessarily for consistency. We have this bounded parameter space, which is lower bounded by theta under bar and upper bounded by theta over bar. There is this limit function Q naught, the red function in the plot, which has a unique minimum at this parameter value theta down here. I depicted it in a way such that this minimum is at the function value of 0, which corresponds to the GMM case. Okay. Now, what we also have is this objective function Q sub t, where t indicates a specific sample size. This is sample size t1. So what the blue line depicts is the value of the objective function, here the GMM objective function for a sample size t1, a specific sample of size t1, and that gives you this shape of the objective function, the blue line. And this blue line has its minimum, this blue curve has its minimum down here at theta hat t1. Now note that if I had drawn a different sample, the minimum of the qt1 function would be somewhere else. This is a particular realization of this qt1 function as a function of the sample that we have. But you should see this as a random function which depends on the sample, and hence the minimum of that function also depends on the sample. Now what happens if we increase the sample size to say t2, say, we get this black objective function evaluated at all values of the parameter space. And what you're going to see is that these the black function and the red functions, the Q naught function, resemble each other pretty nicely. No, they don't entirely overlap, but they become very close to each other. And accordingly, the minimum of this black function, this theta hat t2, is pretty close to theta. Right? If the functions resemble each other, so should the minima of these functions. And that's an illustration that we refer to as a convergence of the qt function to the q naught function. It's a convergence of a random function evaluated at different parameter values, so we need to extend our view on stochastic convergence, and for that purpose we have introduced the notion of stochastic convergence uniformly. And this uniform convergence is basically concerned with those, intuitively speaking, largest differences between the qt functions and q naught. These are these suprema that we've depicted in the plot. That is, at this point down here somewhere, that's the biggest sort of difference between the blue curve and the red curve across all the values of the parameter space. It's supremum, though it's the smallest upper bound, mathematically speaking, of that difference. And for the larger sample size, we see that the supremum, this biggest difference between the qt function and q naught function, is somewhere down here, and we see that this smallest upper bound is much smaller than for the blue curve. And what should happen when we talk about uniform convergence of random functions is that these supremae, they converge to 0, and they converge to 0 for all possible realizations, all possible samples, and this is why we talk about a convergence of these supremae almost surely. That is, with probability 1, it happens that the sequence of suprema have a limit equal to 0. Okay, I tried to explain this idea of uniform convergence in the lecture. What we're trying to do now is we try to formalize the idea that if you have such a specific convergence uniform convergence, we can actually claim that consistency happens such that the sequence of estimators, the theta hats, converge to the true counterparts theta. It should be intuitively clear from the plot that such a convergence happens, but what the proof does, it shows this formally. But it helps very much to understand what the intuition is behind this formal proof when you take a look at this plot that we have here. So to formalize the proof, let me go back again to the lecture notes. This is the last part of the notes that we wrote down in the lecture, where the notion of almost sure convergence uniformly of the qt function to the q0 function is properly defined. So what I said with the words is now depicted formally here. We have this convergence almost surely of the sequence of suprema. So whatever the sample is, whatever omega is, this convergence to zero happens. Now it's convenient to abbreviate this sequence of suprema with this qt symbol down here. So qt of omega denotes the sequence of supremae that we're going to take a look at. Now, if you recall the formal definition of almost sure convergence, here it is repeated for the specific sequence we're going to take a look at, namely this rho t sequence or the sequence of suprema. And here we have in this statement we have the precise definition of almost sure convergence for this specific sequence of suprema at our hand, and I'd like you to remember this definition and keep it in your mind. So we fix some epsilon star value, which is an arbitrary small value, which is bigger than 0, and we can find a cutoff point t star such that this supremum, the difference between the qt and the q0 function over the parameter space, is actually less than this epsilon star. And this happens, right? And if this holds true, then after the cutoff point, so sample size is bigger than t star, the sequence of supremae that we have is actually has a value less than epsilon star. Okay. So we say that qt has then converged to q0 in a uniform sense. Okay, that's the definition of almost sure convergence uniformly. And the point of the consistency proof is now, if you have this specific kind of stochastic convergence of this qt functions to the q0 functions, along with the other conditions like the unique minimum of the q0 function at the true parameter values theta and the compactness of the parameter space, you can conclude, if you have these assumptions in place, that you can actually claim that your extremum estimator is consistent and even in a strong sense. So theta hat t, remember, is the value that minimizes the qt function, converges almost surely to the true parameter value. So we have consistency in place. The point is, this needs to be proven mathematically, not only intuitively with a plot, and for that purpose I'm going to rely on a consistency proof that you're going to find in Singleton's book. There are a couple of other consistency proofs out there which you can consider, but this proof has the advantage of being very brief, very succinct, and very elegant. I think it uses what we call a triangle inequality, and I think it's a very clever way of thinking about proving consistency for this class of estimators that we have at our hand here. Okay, so let's see how this proof works. Well, the starting point of the proof is, as a matter of factly, an intelligent choice of this epsilon star value, which is, remember, should be an arbitrary small value that's bigger than 0. So the starting point of this consistency proof is a clever choice of epsilon star. Okay, and this clever choice goes as follows. Think about a small value that comes from the following idea. Think of the limit function q0, which you evaluate at some value theta tilde, and compare it with the value of q0 evaluated at theta. Note that theta is the true parameter value. This value, per assumption, minimizes q0, right? And it does it uniquely. That's the value that minimizes q0 and nothing else. So if I take another value instead of theta for theta tilde, obviously this difference should be something that is bigger than or equal to 0. So I take some value theta tilde out of the parameter space big theta, and unless I'll actually choose theta, the true parameter value for theta tilde, this difference is going to be bigger than 0, right? Now, what we're going to do is we're going to try to find the largest lower bound of that difference, the inf. So in a way, the smallest kind of difference that you can pick out, by choosing theta tilde out of the parameter space. Now, from what I said, obviously the pick that gives you the smallest difference would be to pick theta for theta tilde. So that would be the inf, right? 0. But I'm making a little constraint here. I'm saying, okay, you pick the infimum, but there's a constraint that you have to obey in the sense that your pick of theta tilde has to be a bit away from theta. So the absolute difference of your pick, theta tilde, from theta, that should be at least epsilon, where epsilon is some small, arbitrary small number, as usual. No? So this is not 0. If it were 0, then you would pick theta tilde equal to be theta, true parameter value, but no, you can't. There's a certain difference that you have to obey here. Okay, so the inf, the smallest, the largest lower bound of this difference is not 0, but it's some positive number, and this positive number will be denoted rho of epsilon. This infimum obviously depends on my choice of epsilon. Okay, so I call it rho of epsilon. A rho of epsilon is some value that is something that is bigger than 0. Some small value that is bigger than 0. Now it's worthwhile actually expressing this statement in terms, right? In words. If you choose theta tilde out of the set of possible values big theta, such that your choice theta tilde is at least epsilon away from theta in absolute terms, then the difference of the limit function evaluated at your choice and the limit function evaluated at theta, which is its minimum, so this thing is bigger than or equal to 0, cannot be made smaller than rho of epsilon. Okay. But from that result, or from that logical result, we can make another conclusion. And I like it to write it in a different letter. If you find actually a value, call it q theta star, which you plug in the q naught function, and you compare the function value with the q naught evaluated at theta, and you happen to find out that this difference, which is obviously something that is bigger than or equal to 0 as usual, if you find out that this difference is actually smaller than this rho of epsilon, what you can conclude is that this theta star object obviously is closer to theta than epsilon. Okay, and this is what we're going to need from the proof. Okay, if this difference that you find, that you evaluate on your at your choice theta star, is actually less than rho epsilon, then you can conclude that this condition obviously is violated. Your theta star is closer to theta than epsilon. Okay, so this is an important insight to understand the proof. Yeah, so this is going to be a very important result to keep in mind, and a very important conclusion that we'll come back to later. Okay. Now, what I've done is I pasted the definition of almost sure convergence uniformity of Qt to Q naught here, and I recognize that there was a small notational error down here. Up there I said that epsilon star was less than 0. I think I didn't say it, but I wrote it. Make sure that you have also in your note that epsilon star is bigger than 0, of course. Now, this was a definition of almost sure convergence uniformly, and now what we do for the consistency proof, we're going to make this intelligent choice of epsilon star. Now let me repeat what is standing here with an intelligent choice of epsilon star. So I'm saying that there exists a t star which is now a function of epsilon, not epsilon star, maybe write it in red, of epsilon and omega, such that this sequence of suprema, which we denoted with this rho t, and I like to write rho t of omega here, such that then this rho t of omega, the sequence of suprema, is less than epsilon star. And for epsilon star, now comes my intelligent choice. I'm saying, okay, this is a small positive number. Let's use rho of epsilon, which you just defined, divided by 2 for this small positive number. Okay? But now this small positive number depends on my choice of epsilon, which defines this maximum difference of theta tilde, for your theta tilde choice from theta that we allow. Okay, here is my small positive number. That actually is that's my choice for epsilon star. Okay, so going on here, this has to happen for every t that is bigger than this t star number, which I say, well, now it's a function of epsilon. Okay, and of the omega that I have at hand. Okay, so just a rewriting essentially of the definition of almost true convergence uniformly, but with the intelligent choice of epsilon star, which is then associated with the difference of my pick of the parameter value theta tilde, and the maximum difference that I allow for this theta tilde compared to the true parameter value theta. Okay? Did nothing basically new or innovative, just an intelligent pick of epsilon star. Now what you can write, as well as saying, okay, you can say that essentially twice rho t is less than rho of epsilon for a sample size t which is bigger than t star of epsilon and omega. Okay, remember what rho t was. It's the sequence of suprema. Okay, and that's a convenient condition, as we shall see below. Okay. Now comes the essential of the proof. Consider that we actually are in a situation that t is bigger than t star of epsilon. I suppress the dependence on omega here. We have a specific sample at our hand. We found this t star cutoff point, and now we have a sample size which is bigger than t. Now, what we can do is we could compare the value of the limit function q naught evaluated at the estimate theta hat t, the value that minimizes the objective function. So it's the value of theta tilde that we choose that minimizes not q naught, right, but qt, our objective function. Okay, but this value is plugged in the q naught function, and we're going to compare this with q naught evaluated at theta. Now, obviously, this is something that is bigger. That difference is bigger than zero, because q naught is minimized by theta, and evaluating q naught at theta hat should give you a higher value of q naught. Okay. Now, what we can do is we can make a little add and subtract strategy. So here's what I'm doing. I have qt at theta hat t as before. What I'm going to do is I'm going to subtract now qt at theta hat t. This is the objective function at its minimum. Okay, I subtracted, but I immediately add it again. Okay. Next step is I subtract qt, my objective function, evaluated at the true parameter value theta. This theta does not necessarily minimize qt, okay, but I have it in, I subtracted it, so I added again, and I have the term q naught of theta, which is still there. So nothing changed, but I added and subtracted stuff. Now take a look at this part in this sum. We have qt evaluated at its at the parameter values which minimize it, and qt evaluated at some other parameter value, and only if theta hat t would be the same as theta, this term in brackets would be actually 0, but generally this term in brackets should be less than 0, or if you allow for theta hat to be theta, it could also be 0. So the term in brackets is the term that is less than or equal to 0. So if I would leave that term out in the equation, so basically if I would write Q naught at theta hat t, maybe I stick to the green, Qt minus Qt evaluated at theta hat t plus Qt evaluated at theta and I have minus Q naught at theta. Okay, a previous line contained an error. That should be a minus. Okay, Q naught at theta is subtracted. Now I left a term that is less than 0 out of the equation, so I can claim actually that the second line here gives you a number that is smaller than this line. No, so this should be less than or equal. The second line should be less than or equal to the third line that we have, right? And now comes something that is referred to as a triangle inequality. Now take a look at this term here. This term, I don't know what the sign actually is. It can be positive or it can be negative. Q naught is evaluated at theta hat. Then Qt is evaluated at theta hat, right? I don't know whether this is positive or negative. I know that Qt is minimized at theta hat, but I don't know the value of Q naught evaluated at theta hat. Could be bigger, could be smaller. I don't really know. And the same thing goes here for that term. That could be positive or negative. I don't really know. I know that Q naught evaluated at theta gives you the smallest value of Q naught, but Qt at theta could even be smaller. I don't know. It's not clear. However, if we take the difference of these two separate, if you take these two differences separately, and would say, okay, let's take the absolute value of these terms, right? And actually, what I'm going to do, and I'm going to reverse them. The elements doesn't really matter. So if I take a look at this term, but I take the absolute term of them, what I definitely know is that when just compare this term with this term, what I obviously could say is that the upper term cannot be bigger than the term below. No. Same thing goes for the second difference term, of which I don't know whether it's positive or negative. If I take Qt of theta and subtract it from Q naught of theta, and I take the absolute value of it, whether it's positive or negative, I don't know. But this term is going to be positive, so that's going to be definitely also that the term on the second line, this guy, is going to be less than or equal to this guy, right? Which means that if I compare this line with this line, I have again an inequality relationship that works for me, in the sense that the previous line gives you a value that is less than or equal to the value of the last line. Okay. But now compare these two absolute terms that we have here. Now, both terms should be will be less than or equal to rho t. Holds true for both. Right. Remember what rho t, how rho t was defined. So rho t was the supremum, the biggest element, or the smallest upper bound of the following set. We compared qt, evaluated at theta tilde, with q naught, evaluated at theta tilde. Okay. Took the absolute term of them, absolute value of them, and we took the value that provided intuitively the biggest difference. Now, if you compare that, the sup is given by your theta tilde choice, but the theta hat, neither theta hat. It could be the case that theta hat and theta corresponds to this value theta tilde that you pick, and that gives you actually this maximum difference. But that is by chance. Any other, if theta hat or theta would not be identical to the theta tilde value, this term and this term as well will be less than rho t, right? And this is the insight that we've gained from this inequality considerations that we've conducted so far. So let us write down what we found. The object that we started with was actually this difference. You see it. Right, this is where the equation starts, which is sort of the left-hand side of this inequality. So what we say is that Q naught evaluated at theta hat t, and compare this with Q naught evaluated at theta, is less than or equal twice rho t. Okay, but what we also already saw up there is that twice rho t is less than rho of epsilon. Okay, now this underbraced results, okay, that is what we have for t bigger than t star of epsilon, right? Recall when we go up to our nodes is that is what should happen when t gets bigger than t star. If you have, in other words, if you have this almost sure convergence uniformly of qt to q naught. But the hitch down there of this result is the following. Okay. So I'm going to restate it. Okay. So I'm saying that Q naught at theta hat t minus Q naught evaluated at theta, this value is less than rho of epsilon. Okay? That's the important statement. But know what this statement means. Okay? And compare it to what we find up there. Okay? Here is the earlier result that I try to copy down. Okay, this is what we find earlier. But what we then can conclude from this red result and compare it with the black result that we have up there is obviously what should be the case is that theta hat t should be closer to the true parameter value in epsilon terms than epsilon for sample sizes t bigger than t star of epsilon. And that is basically what the proof states. Okay? What we essentially can state now is that there exists a t star as a function of the epsilon that we choose, and as a function of the sample size of the omega, the sample that we draw, such that the difference of the estimate from the true parameter value in absolute terms is less than epsilon for all t which are bigger than this t star cutoff point, which is determined by epsilon and omega. And this actually happens, or can be found, this t star point can be found for all omega, and of course for all epsilon greater than 0. But this statement says nothing else but, well, what's written here is that theta hat, my estimate, converges almost surely to theta. Okay, and essentially that's the proof, no? We can write it in a different form and say, okay, the probability at the limit of theta hat t is the true parameter value theta and this probability, the probability for that event is 1, and that is essentially what we're trying to what we wanted to show. That completes essentially the proof. No, this almost sure convergence uniformly of the qt function to the limit function is what is needed to establish almost sure convergence of our estimator to the true parameter value. Okay, it's a strict consistency that we've proven here. Note that the strict consistency also implies a weaker form of consistency, namely convergence and probability. So you may be interested only in convergence and probability, but as a matter of fact, here we can actually show almost sure convergence or strict consistency. Okay, and that completes this consistency proof for extremum estimators. Now note that this proof is pretty general, does not necessarily only apply to GMM, but other extremum estimators as well. It's pretty general, but also this convergence of the limit of the objective functions to this limit function, which is at the heart of the whole proof. That is maybe something that you could argue is something that is a bit technical. Under which circumstances can we actually claim that this specific kind of convergence happens? No. So this is the key assumption that we have to deal with uniform convergence of qt to q naught if this is there, if you can safely claim this convergence to happen, then you can claim that your estimator is a consistent one. It's a very general result, but maybe this convergence of the functions is something that is maybe in some applications questionable, right? Does it really happen like suggested in this graph here, that the objective function and the limit function fall together for large sample sizes? Why does it happen? Why do these functions converge? Why does this Qt function converge to Q naught? There are actually attempts out there which try to specialize this general consistency theorem, which is very general to specific cases, and also to the GMM case. And these specializations essentially recognize that Qt, the Qt function, for extremum estimators emerge either as a sample mean itself, like for maximum likelihood or for nonlinear least squares, or in the case of GMM, that the objective function is itself a function of sample means. And then we could argue that, okay, sample means have a tendency to converge to expectation counterparts, and maybe we can exploit that fact to establish this convergence of the Qt function to the Q naught function. And as a matter of fact, this is precisely what people are doing in order to fashion or specialize this consistency proof to GMM. And I think I'm going to record another video which explains briefly how we can argue that in the GMM context, this convergence of the Qt function to the limit function actually happens, and what is required for this convergence to take place. Okay, this is the end of this video. Make sure that you've understood all steps of this consistency proof. If you have questions and feedback, please contact me. Okay, thank you very much for listening to the video again, and good luck.